Hi guys, it's Rod from VMN here, the home of the Spaceship Plasma. What I wanted to do today is to have a little bit of a talk and maybe a tutorial about how to wire up a Mesa 7i76E for LinuxCNC. So before we start, let's just have a bit of a look at the tools that you might need and some of the additional hardware you will require. So let's start by looking at the 7i76E and beside it a couple of THCAD. One's a THCAD 10, which will be used for torch voltage sensing, and the second one is a THCAD 5, which will be used for ohmic sensing. So I want you to pay attention to the mounting brackets here that are in use because they're Mesa's best kept secret. They sell these little brackets, if I can just get it to focus. Mesa sells these little brackets in packets of 3. They're not very expensive, and when you're ordering your hardware, be sure to grab one of the a packet of these, a couple of packets of them. The THCADs are a different mounting pitch, so that hardware doesn't work for that. So what I've done here is actually, you can see on the corner of the board, I've actually plasma cut a small piece of aluminium, which then has some DIN rail mounts bolted onto it, and then you just buy some standard electronic board standoffs that hold it up. The other thing that I recommend that you get, strongly recommend that you get, is one of these, which is the Mesa COMEX 2, they call it. So one of the things you find when you wire these things up is that you need to have a lot of connectors to field power. So this particular connector bolts on, you can see it's mounted to one of the DIN rail mounts, the Mesa DIN rail mounts, so that means 6 of them are required with a 7i76E. So there's 24 pins on this using the same connectors that Mesa uses on all their boards, and they're broken up into 2 common blocks. So the first one you connect to field power negative, and the second block to field power positive. And you can see that I've used red and green wires here to denote that. So I want you to open a browser, and I want you to get 2 tabs up. And in one we're going to type in Google, we're going to type in my 7i76E connection sheet. Find the page on the LinuxCNC forum. Make sure you're on page 1 and go right down to the bottom here of the first page, and you see that I made a typo error here which Norbert fixed. So get the one from the bottom of the page, and then in the other one I want you to type in 7i76E manual. And you see here we've got a PDF, and just check that it's at MesaNet, so you're getting the current, latest, everything there. And now we've got all the information we're going to need, and we're going to just flip down here quickly to give you a little bit of background. We just want to go down until we get to connect to 5 volt power. We're not going to use 5 volt power. The only time we're going to use 5 volt power is if you've got additional devices plugged into the 7i76E that need more current than what the built-in regulator can supply. But what we want to do is get down to this IP address selection, which we talked about earlier. So you can see by default the fixed IP address is 192.168.1.121. Now the recommendation is to change W3 to be up, which it says fixed from EEPROM, and that will allow us to set that 10.10.10.10 IP address that we wanted to set. And we'll go down here a little bit. I might be able to make that a bit bigger. So it's pretty daunting to tackle this without any help. But if we take Norbert's connection sheet, he actually shows you the commands that are required to configure this, except we're going to change that Etherbook IP to be 10.10.10.10.10. So board IP, change that. Num encoders, if you're setting up a plasma machine, you will change that, but we need to run some different firmware. Or you may change that, but we need to run some different firmware. Number of step gens, more likely than not, is going to be 4. So that's all up here. So then we get down to this here, W3 down by default, but we want W3 up. It's suggested to use the 10.10 IP address for LinuxCNC so you don't end up with the real-time Ethernet address range overlapping a DHC pool of local network addresses. Set W3 up instead of down. So now we're at the time to start connecting some power. So I would strongly recommend that you orient the board in exactly the way that it's shown in these diagrams, and it shows here that this is field power, and we need it to connect to that one and the 1, 2, 3, 4th one in, and also to bridge the field power across to the 5 volt area where it will power the rest of this board here using the onboard 24 volt to 5 volt regulator. So let's have a look at that. So the other thing I found very useful, which I didn't know about when I first built my Spaceship, was how handy these DIN rail terminal strips are. And there's all different kinds. This one here is green and yellow, is an earth which then will clamp back to the DIN rail. So it's very handy for earths. This one here has the ability to put a fuse in there. And you can get these little terminal strips, little connectors that you can trim a few off, and you can use them to bridge common blocks together. So whilst we've said use the Mesa common block, you could use a heap of these to achieve the same result. But in my mind, the other one is more compact and much easier to use. So the very first thing to consider also is your power input. And what I'd recommend, and I wouldn't say this is the right one to use, but what I would recommend here is a IEC connector. Probably has a power switch built in, probably has a switch, a fuse in it, and the big thing is that this will reduce or totally eliminate noise entering your control panel. For high-powered connectors, it's hard to go past the, I think they're a GX16, but they're basically a microphone connector that you see, aviation microphone connector, which you often used to see on CB radios and the like. This is a 4-pin one, but I like to use a 5-pin one so that I can pass the shield into the control box and terminate the shield right at the stepper motor controller or the drive controller. In fact, the drives that we use actually have a spot to terminate that. So personally, the 5-pin is a better option. The other thing you probably should consider, but maybe for home use or do-it-yourself build, not so essential is a safety relay. Now essentially what this does, this cost me Australian dollars $250, so they're 100% compliant with all the relevant national and international standards, and what they do is basically allow you to trigger a motor contact or a mains power contactor or three-phase motor starter and wire off your e-stop, so it's 100%. Everything is compliant, so your e-stop chain will run off this particular thing. So probably not necessary for home build. In our case, what we're going to be doing is using a toroid power supply. This one is one that I had custom made, and it will output 60 volts at 12.5 amps. And the reason why there's so many additional wires here is that, as well as the output and input, this one is has the ability to be driven by either 240 volt power or 110 volt power, depending on the wiring that you choose. So that is what will be powering our motor drivers. We're not going to step this down to DC. We're going to leave that to the Lamb Technologies drivers to step that down. So they'll get 60 volts and give the motors almost 90 volts. So we're really going to hammer the motors once we get this all together. The other thing is a recent find, actually, is I got this off eBay and it only cost about $40, and it's a ferrule bootlace crimper. So I never had much success with ferrules before, these bootlace crimpers, but this has made it so much easier, and they actually work now. So this kit, I'm running out, mostly it's the little white ones, I'm running out of them, but I've used them everywhere where I can. And then obviously you'll need a screwdriver, some wire cutters, screwdriver on the floor, and some wire strippers. A good set of wire strippers here is really worth their weight in gold. So that's basically the hardware that we're going to use. So what I'm going to do is just bring the 7i76E over into a bit closer focus and show you what I've got here, if I can. So here I've got my terminal strips. We're actually going to have 3 power supplies off this. So I've got the mains power coming in here with its ground going to the green and yellow terminal strip, which is grounded back here and then in turn to the enclosure. Each side of that I've got neutral and active, and they've been hooked together by some of those little terminal connectors. So basically there's enough wires on here with a spare set still over this side to run my 3 power supplies. So that is the toroid, which we saw earlier. This one here is a 24 volt power supply. It's not a particularly big one, but it's 1.7 amps. So that's probably enough for, it's probably enough. I don't know if I can focus on that. So MDR 4024, that's probably more than enough. And this one here is a smaller, I think they're I've got to get this right, I usually know them off by hand, but this is my independent isolated power supply for ohmic sensing. So it's a HDR 12 HDR 2415, I think, so it's about 1 amp or something. 25 volt, 0.63 of an amp. 24 volt, 0.63 of an amp. Just when you deploy it, just make sure you adjust the power using a multimeter here with the adjustment screw. So that then has all the power and everything, all the hardware set up, ready to go. So on our field power, what I'd suggest that you do is neutral and live come in here from this block here, and over here we've got your 24 volt out. We've still got another 2 connectors here, but we don't really need them because we're going to put that power straight down onto our little bus bar here, and you can see we've got one here on to be the negative side. So from here back is negative. You can see I've used a couple, and from here back is positive. So this is going to make it really easy to connect hardware, which we'll see shortly. So before we move on to the next stage of setting up our 7i76E, I want to spend a little bit of time talking about basic networking, because it seems like a lot of people struggle to get this right, mainly because they don't understand the basics of a TCP IP network, which I'm sure you know drives the whole of the internet. So let's just stop for a minute and we'll have a look at a bit of a drawing. So I'm not sure how we'll go here drawing on a side, but just think about your normal network. You've got the internet out here and you run in through a modem or a router to your home network, and then all your PCs are generally attached to that network. And sometimes you'll have Wi-Fi coming off here as well. So generally this network is in the 192.168.x.x range, or .0. So what happens here is that your ISP will normally allocate an IP address to this, and that's a real live IP address that's able to be seen anywhere on the internet. So it has to be a live one. So back here is the rest of our network. Now, the internet doesn't care about that, and what they came up with when they invented it, the internet back in the early days, they said, let's allocate some fixed IPs that are some IP ranges that will never get routed out here to the internet. And one of them is 192.168, and the other one, or there's another two, there's the 10.0.0.0 network, and there's another one called 172.16.0.0. So none of those, if anything out here on the internet sees any of those IP addresses, it'll just drop the packet. It says, no, it doesn't exist. So one of the things about your network is that it has a gateway, which is your address on the internet. So if you have your PC out here, this might be 192.168.1.12. So it's that. So that's that interface there. And it knows, when you set your network up, it knows that the gateway is at, say, 192.168.1.1. So that's this IP address here. So it knows to get anywhere other than 192.168.1. So any IP address starting with anything other than 192.168.1, it knows that it's got to ask the gateway to forward it. So normally we're going out to the internet and the gateway or router sends the traffic out here. So in our case, what we want to do is add a 7i76E out here on its own separate network. Now, there's lots of ways you can do this, but the standard recommended way is to configure this to be a 10.10.10.10. And we'll make this one a 10.10.10.1. So this allows the 7i76E to have a dedicated connection between your PC running LinuxCNC and itself. Now, something that's interesting about this is that we don't give this network a gateway. So it says, oh, well, all I can see is any computer or any device on the network starting with 10.10.10.x, right, for 3 tens. So traffic on this segment will not go past this because it doesn't know how to go. If you then said, we want the gateway to be 1.12, it then would be able to send traffic out here. But we don't want that to happen. We want this to be locked to its own devices. So that's what we're trying to do. Okay, so now we've covered all of the basics that we need. It's time to get going. So what I want you to do at this point is to head over to a browser, and it's really handy if you can do this with the right in front of the 7i76E. So maybe you're using a browser on the computer you're going to configure for LinuxCNC. But let's have a look at it on a monitor for now. So here we go here now. Remember, we got all this area here fully configured and we're happy with that. Remember that we've got our common connector here configured, so one half is negative from here and the other half is positive. So then this then becomes really simple. Okay, so over here, in accordance with that, you can check me as you do this. So we've got our negative coming in here and we've got our positive coming in here exactly as per that diagram. And then also from over here, we're powering the 5 volt section exactly as it was shown in the diagram. So now we have this all set up. So at this point, it should be quite happy to be able to power the machine on, or sorry, to plug the Ethernet connection into the device, into your computer, and power up this side of it. So I've just opened up the back of my very much work in progress HMI enclosure, and eventually down here, I've just got one here for now, but that one goes out to the 7i76E and it's patched out, and I've put this label on it, which I think is a good idea, because once you set up the network, you want to know where to plug that one in. So, and this one is just going through the hole here, goes out to the main network. So this is the 192.168 IP address we talked about, and this is the 10.10.10.1 IP address that we spoke about later, going out here. And this one here, more on this later because I've still got a lot of work to do here. I have the 7i73, and ultimately I'm going to have a board that plugs into the 7i73 that connects everything else up for me, and the other component I'm going to add is a pendant control. So should be able to see that there. So pendant control will be hardwired in and to the 7i73, and I've used one on my 7i76E for a long time, and I really like this. It's expensive, but I just find it's 100% reliable. I read a lot of problems with people using USB USB pendants, and I just didn't want that on a fairly large plasma table. So that's going to go in there. But, oh, there's one more thing I've got to do, and that's find some power. Ultimately, as I spoke about, ultimately I'll have the have this here being the IEC connector with the filter and main power switch, and I'll need that to power the monitor. So there'll be some wires going out to the monitor, and somewhere in here I've also got to mount a 15 volt power supply for the Odroid H2 Plus, which is this one here. That's actually a computer. So I'm liking these little computers. I think they're the way to go. So just a quick interlude while I brought power in here on a temporary basis for both the Odroid H2 Plus and the monitor. The monitor plugs into an IEC connector down here. The Odroid is over here. And the Odroid's configured to boot on power, so hopefully when we turn this around we should have a monitor display. Okay, it's the moment of truth now. The PC came up nice. All I've got to do now is power on the 7i76E, and hopefully it will become live. So if we open a terminal, we should be able to ping it. Beautiful. So we know it's there, and we should also be able to ping our router, and we should be able to ping something external to the internet. This one is an old Telstra DNS server or something that I remember from years ago, and I've used it for about 15 years just to test that things are happening. So that is perfect. So what we need to do now, we're running Linux Mint, what we need to do is just duck over and find our network. It's a bit hard to see from under network connections. It's a bit hard to see here, but I need to look at IPv4 settings, and this one is the main network out, and that's showing it's automatic from DHCP. And number 2, if we go over to IPv4 settings, you can see that I set this manually to be 10.10.10.1. And there is no gateway, so it doesn't know how to get out to the internet. So that's what we need. So now we need to run a script here to say that all that command there is when you do a run in place, it actually sets all the environment variables up so that now we can find LinuxCNC. So typing in LinuxCNC, when you're doing configuring, always start LinuxCNC from the command line, because when you do that, it will show you any errors will print here. So I've got to run my configurations. I've done a really basic one here. My LinuxCNC machine. When I set this up, I never bother. I just run PNC CONF to actually get the system configured. But in terms of calibration and everything like that, I'll do that manually in HAL. So if I run if I find Genie, under configs, my LinuxCNC machine, HAL. Bit hard to see from 4 foot away. But you can see here that I've previously set the HAL file up here. A number of encoders is 3, so that's the other thing that we have to do. I'll deal with that in a minute. So what I want to do now is to demonstrate how to trigger an output, an input. So if you have a look on Norbert's connection sheet, you'll find that inputs start here, and while the pins are numbered from 1 to 24, the inputs are actually numbered from 0. So we're going 0, 1, 2, 3, so 3, and we're on input 4. Now, these first 4, I made this mistake. These first 4 are analog inputs. So I'm going to use them, you can still use them as an input, but I'm going to use them last. If I need a pin, I'll use them, but for now we're going to start here at input 4. So if we take an ordinary limit switch here, this is just a simple switch. So if we take this simple switch, what I would normally do is get a multimeter with a buzzer and buzz this out and understand how it works. So I know that that's a common connector, and this is normally open on that one and normally closed on this one. So all we need to do now with this connector, or with this switch, is to actually come over here, and this is why I like this one in the mix, is the other end of the switch. We just need to pick up field power, positive field power. Sorry about using a red wire, but we've got positive field power here going into field power. So what's going to happen now is that power will be able to run around this circuit, go out into the input, light up the input, and go across to field power ground. So just out of view. So that's the circuit that we're going to do, and we said we're using input 4. So if we go up to HAL show, and we've got input 4 here, and it should trigger. So I click this, and it should trigger. So I hope you can see that. Yes, we can. So all good. Now, the other thing that Mesa does, and I think this is fairly common with most input forms, is that there's also an input for not. So this one here says is true and gone yellow because it's not connected. Does that make sense? So one is the inverse of the other. So we'll see this as we switch this, we'll see them change. Now, sometimes you'll need to use the not pin, sometimes you'll need to use the input pin. So it's just totally dependent on that, but that's the simplest explanation I can give you on how to wire up a pin and how to take a methodical approach. We haven't done anything with HAL here now yet. All we're doing is using the LinuxCNC diagnostics to make sure that we know where that pin is, and we know that we've got it wired up correctly. So now we know is that for if we use that pin by that name that you see on the screen in HAL, we'll get the right option. So if this was a limit switch, then what we would do now is in HAL we would connect that to, say, min limit X or max limit X. So very easy if you take that slow and methodical approach. So the other input that you might use is a proximity sensor. Now what happens there is there's 3 wires here. So one goes to plus field power, one goes to minus field power, and the third one is the output. So what I do every time I use one of these, I can never quite remember, I just Google proximity sensor wire color and I look. That diagram is probably as easy to understand as any. What it's telling me is brown is positive, blue is negative, and black is input. So I'll just stop the camera now and we'll quickly wire that up and we'll be good to go. So now we've wired up our proximity sensor. This is it here. Blue, we said blue went to negative, brown is to positive, and black, the signal goes through to the input. So we've now run that back over to the input and we've used the next sequential one. So so that just leaves us now to test it. And so I've just got my screwdriver here, and what will happen is when I bring the proximity sensor there, you'll see that the LED lights. Now what we need to do is test to see if that does it on the screen. So now we're going to prove this here. We've wired that up to the next connector in the session, so that will be input number 4. So if we bring this in line, if I can bring that up somewhere so you can see it, once the LED lights, input 5 will trigger. Bit hard working backwards. Now we've used for 7i76 we've used a PNP proximity sensor. Make sure you get PNP sensors. If you do what I did and got the wrong one and got an NPN connector, you'll need to add, say, a 2.2K, I think I used 2.2K pull-up resistor back here. So what does that mean? Well, back where we did these, if we can zoom in, you need to connect a 2.2K resistor from the input through to plus 24 volt. Pull up we want. So plus 24 volts. If you're using a 7i76D, then you probably use an NPN connector. It's just 2 different ways of working, but wherever possible, unless you're trying to work with a retrofit, definitely use a straight ordinary 7i76E. So that's the good oil on inputs. So what I thought might be a bit of fun to do now would be to show how to connect to an output. So I've got this little solid state relay here. I've been using quite a few of these. They're 6mm wide, they're reasonably priced. You get them from Radio RS Components, and they cost about $100 for a box of 5 of them. So they're very handy to have. And the other thing I like about solid state relays is that they have an extra layer of isolation when we're dealing with plasma cutters. The other good thing about this is that they have an LED here, and that'll be useful for us here because that'll show us that we're triggering the relay from within HAL and we haven't got anything else connected to it. We're just demonstrating the use of an output. So, so how simple is this? On the 2 wires here, the black one here, we're just moving the black one and connecting it across to our normal field power. So we've moved it up here to where we've always been working, and we've connected it to this pin here. So hopefully we can see that. Am I in the shot? Yep. So to this pin here, so that wire there is going to field power negative. So what we're going to do here is take this output wire here, and we're going to put this to an output on the 7i76E somewhere over here. Somewhere over here. So that's pretty simple to do. So all we have to do, I've checked this in before we've done that, and there are 8 outputs across the end of this, and they're counted or numbered from 0 to 7. So the last one is output 7. So all we're going to have to do is to take this wire and connect it to output 7. Fantastic. So if we open up HAL and open up our HAL file, by default there's a pin there called spindle.0.on, and it's connected by default by PNC-CONF to a signal called spindle-on. So all we have to do is connect spindle-on using a net command to our output number 7. And what that will let us do is we'll be able to trigger this relay on and off using an M3 and an M5 command just for the purpose of the demonstration. So we'll just pause it here and we'll see if we can get the screen up, and we'll keep going. So here we are in HAL, and there's a custom, so there's a standard command put in there by PNC-CONF called spindle enable, and it's coming from LinuxCNC spindle.0.on. So that's part of the motion command or motion component. So all we have to do is connect that to our output. I'll see if I can find that. So here we go here. So we're doing a command here, net spindle enable send to 7i76E output 7. So if we save that, then we should be good to go. Let's do that and see what happens. So we'll run LinuxCNC /L from the command line, and hopefully this will open for us. Then we need to do a bit of homing. Turn the machine on. Turn the e-stop off. Turn it off. Turn the machine on. Home all our joints. 1, 0, 1, home. 2, home. 3, home. Everything is now homed. You see everything came up there. So now if we go to the MDI prompt, which is another tab, if we type M3, I'll just do this to make sure, and M5, this will turn on and off. So here is our relay. There's our relay there. So M3, that should turn on. Go. And you can see the light came on, and I'll trigger it off with an M5. Now, that's just a really simple example. The 7i76E has a spindle control on as standard, so we actually don't need to use the relay to turn a spindle on. We can use the onboard stuff. So, but that's just a nice simple way we can test something from HAL. So using the spindle relay, but you can see how easy it is if you take a logical approach to wire up your machine. So one thing I may not have clarified about this relay here when we were playing around with the M3 and M5, the spindle on signal, is that this is an opto isolated relay and there's no inductive loads in it. So if we were to take a more conventional relay, such as this panel relay, we have to protect the input against damage. And the other thing that needs to be treated the same way is an air solenoid. So let's have a look at what we've done here to protect that solenoid from being blown up. What we've done is that these two wires are the input to the solenoid, and what we've done is we've put what they call a flyback diode around it from those two terminals. And once again we've used a green wire here for the to connect it to the output. So what's important with this is that the band on the diode needs to point back towards the output. So and you would do the same with an air solenoid as well. I haven't bothered to connect this one because it is the same, but essentially you need a flyback diode on this because it also has a coil in it as part of the solenoid. So these inductive loads can blow an output if they draw more than about 60 milliamps. What I thought I'd do is use a digital output. So there's a pin called motion digital out 00, and we can trigger that on and off from within G-code. So once again we've taken that that pin name, which is motion digital out, and we've created a signal called DIO-0. So basically we've connected one end of the signal to this output in LinuxCNC. So the next command takes that DIO-0 and connects it to output 06. So what that will let us do is turn that on with an M64P0, and we should just be able to hear that solenoid trigger when we hit that button here. And to turn it off, we'll go M65P0. So if we move the camera here somehow, we might actually be able to see the go. M64P0 should turn it on. Listen and watch. And then turn it off, M65P0. So that's just a really simple demonstration. So just in summary, what we've seen so far is we've connected the we've talked about the various types of inputs. We've shown how to deal with switches. We've shown how mechanical switches. We've shown how to use a proximity sensor, and we've shown how to trigger a couple of different types of outputs using HAL to connect the signals to the pins. I can't stress enough that it's really important to take a really logical approach with this. And whilst I've just gone in and done this, what I recommend, until you really get confident about it, is that you move one thing at a time. You find the signal in HAL show that you want to change. You confirm that it will change when you do something like our M4, M3, M5 and our digital output. And then you connect it, and then you watch that you see that working, and then you connect the hardware And if you do it that way, you'll have little chance of getting something wrong. So the only thing we've not really talked about so far is how to connect a THCAD to the equation. So that'll be probably the last thing that we need to cover.